microwatt. So I'm substituting for Professor Chu today. He's got a meeting, so he said you guys what you finished was the node voltage method and loop current method last time. So we're gonna basically you guys are scheduled with a course calendar. So we're gonna do a superposition and linearity today. So to start out with that, what I'm gonna do is basically start with the circuit, and what we're gonna do is analyze it again using the loop current method, and then we'll see what happens when we get the final solution, and relate that into the next topic. So if you guys remember for the loop current method, then what we should do is start assigning loop currents, right? So if we look at this particular circuit, then what I can do then is so let me choose this to be current 1. So this is going to be my first current. Let me call this I2, and then this is going to be I3. So I have my 3 loop currents there. And I don't know exactly if Professor Chu followed the course notes directly or not. The way I've been telling this in my class is the next step, the good thing to do is to always assign polarities and current directions to all elements. So that way, once we write the equations, it's very easy to follow what voltage we follow, what direction we follow. Otherwise, you might get confused in the middle of the analysis, and then you get the wrong signs, and everything goes wrong. So I personally then try to always the next step after setting up the loop currents then is choose directions for currents and polarity. The voltage source, of course, already has polarity there, so I'm just going to put the current coming into that same positive terminal. And then on this resistor, I'm going to choose a plus minus like this, and the current's going to be coming into the positive terminal. This dependent current source already has a current, so I'm going to put the plus minus, so it's coming into the positive side. The current source, the independent one, also has already a direction for the current. The plus minus there. And then for this resistor, let me assume that the current is coming into this side with a plus minus like this. And then for the 2 ohm resistor here on top, and then you do a plus minus here with the current coming in out there. So basically, once I set that up, then it's very easy for me to write the equation because everything is clearly set up, right? So then I also, when I look at this, what I recommend is starting then with current sources, because the current sources provide you the easiest equations that you have. In this particular case, we have 2 current sources. So if we look at, we have this independent current source. So you can write an equation for that independent source based on the 2 loop currents. One of them is I2, which is over here, because this one is going to come this way against my source, whereas I3, we follow this, I3 comes in the same direction. Right? So I have one going against my source, then one coming with my source. So then I can write an equation that IS, so my current source, is going to be equal to I3, which is coming in the same direction, minus I2. So it's a very simple equation I can write, and it only involves 2 of the currents. So that's as easy as it can get. Then I have the other source, which is dependent, but it's still just a current source. So I can write it again in terms of I1, which is coming in the same direction, and then I3, which is coming in the opposite direction. So I can write in an equation for 2ix, which is a dependent source, and that's going to be equal to I1 minus I3. So I have, again, another simple equation. It only involves 2 other loop currents.
Aside from IS being a variable, is this going to be any different than what we were taught yesterday?
No. It's actually not a variable, just I haven't given you a specific numeric value. It's not a variable. It's just going to be fixed. So, yeah, it's just a current source. It could be 2 amperes, 1.1 amperes. It's fixed. I'm just keeping it as a symbol because it's going to be easy to transition from there to the superposition concept. So just for now, just think of it as just a number, it's a fixed number. Yeah, so it's exactly the same thing. And then once we have those, then what we should do then is do KVLs, right? So the loop current method, what you do is you use KVLs on these loops. Now, if you guys probably saw then the super loop concept, right? You guys saw that? So the super loop concept is once you have these current sources, because I'm able to write these simple equations that I have up there already, then I can basically avoid going through a KVL on this first loop, for example, if I did a KVL on this loop, then what's going to happen is I'm going to have to introduce here a new variable, say let's call this Bx, because I don't know what's the voltage in that source. Right? So then if I write an equation for that loop, then I have 3 equations, and now I have 4 unknowns. So it's still going to have to. So every time I do that, I have to introduce a new variable. The same thing if I do that on, if I do a KVL over here, then I'm going to have to assign here another voltage, say Vy or something, because I don't know the voltage in that current either. So I just keep increasing the number of equations that I'm going to need to solve this problem. So what the loop does is realize that, well, I don't really care about that voltage anyway, because I already have some equations that relate to those sources. So what it does is, it says you can just bypass the current sources and do something else. Basically, what I'm going to do then is avoid going through the actual current sources, but I still need at least one more equation to do this, right? So a natural way to choose a loop for this is if I go here and I start out all around the outer loop. And that way I skip both current sources. And then that way I don't have to write any Vx or Vy or anything else. I didn't introduce any new variables. So that's why the super loop is helpful, because it reduces the number of variables. Then I'm going to write an equation around that big loop. And so let's write that equation. So what I'm going to have then is for that one, if I start, say, down here at the bottom, so what I'm going to do is if I'm a charge and I start down here, right, so I'm going to gain, because I call it -2 plus, and then I'm going to lose over in this resistor, I'm going to lose over in this resistor. So I gain once, and then I lose twice, right? So I'm going to gain Bs, so that's on the gain side, and then I'm going to lose then 2, and then the only current that's going through that 2 ohm resistor on the top is I2, so I have I2. And then on this 1 ohm resistor here on this far right, then I only have I3 going through it, so I have plus. And here, I know it's redundant, but let me write 1 times I3, so we know it's the voltage from the resistor. So now I have 3 equations, so I have 3 loops, and I have 3 equations, but I have 4 unknowns, right? So that doesn't seem right. But the thing is, that the reason why we have a 4th variable there is because we have a dependent source. It's not because the method is failing, it's because we have a dependent source. So that dependent source depends on something else. It's a variable. And so whenever you have a dependent source, you are going to have to look for another equation. And in this particular case, it's fairly easy because this depends on Ix, and then Ix is the same as I2. So we have a very simple equation for that. So we just write that Ix is equal to Y2. 4 equations, 4 knowns, we should be able to solve this. Normally, what you want to do is reduce the equations, and so you just want to leave them in terms of the loop current. Right? So in this case, wherever I have an Ix, I should substitute it, which is just here. So it will be easy. Now, once I set this up, then what I'm going to end up with is 3 equations that look like this. I'm going to skip sort of the algebra, but what we're going to have is that Is, so this one we already had, which is minus I2 plus I3, so I'm going to write it in the same order here. Then I'm going to have 0 from the second equation. Once I substitute the Ix, then I'm going to have I1 minus 2I2, then minus I3, and then the last equation I'm going to get is Vs is equal to 2I2 plus I2. So those are the 3 equations, and all I did was I just rearranged the terms so that all the loop currents are on one side, and I got rid of Ix. So I have a system, the 3 loop currents are there, and I can solve for this, right? So you probably then already know that this is a linear system, right? So here we have I1, I2, and I3, just as linear terms, right? So they just have coefficients and they're being added or subtracted. And that same thing happens for all of the 3 equations. So these are linear equations in terms of the loop currents. So you guys probably saw how to solve this already. And now the nice thing about this is I'm not substituting the values, because once you solve for this, so let me solve for this in terms now of the constant, right? So here we have an Is, and then here we have a Vs. So the solution is definitely going to be involving those two variables, right? So let's see how the solution involves those two. So if you solve for this, then what you will get is that you get that I1 is equal to Vs. You're going to get that I2 is equal to 1/3 Vs minus 1/3 Is. And that I3 is equal to 1/3 Vs plus 2/3 Is. So that's my solution. Of course, if I give you values for the voltage source and the current source, you can immediately get some numbers out of it, right? But the important thing here is that I actually don't want you to look at the numbers. I want you to see how this is related to the sources. So if you see the first one, here I1 is Vs. There's no Is, it's only Vs here. But if you look at the second one, you have Vs and then you have Is. And the way they come out, they're not mixed, right? They're completely separated. So they're linear in the sources as well. So not only are the equations that we have linear in the original variables, but once you solve for it, the solutions are linear in the sources. And not all the sources, just the independent ones. See, the dependent source went away. It doesn't show up. So what happens is, with both the node voltage method and the loop current method, your solutions will always be linear combinations of the independent sources. Always. So that's the very nice thing about those methods, is that what it shows is something we're going to call the superposition principle, and I'm going to write this down there. But what it says is basically, because there's no relation here, if you look at this term, there's no mixing between Vs and Is, so I could potentially just forget that there's a current source, so basically get rid of this term, for example. Just solve for that system just with a voltage source, forget that there's a current source, obtain a solution which is going to be this term that I just left there. And then afterwards, what I'm going to do is I'm going to get rid of the voltage source and just think that there's just one current source, and then I don't get this term, I only get the other term. But you already have the other one, then I add them together. So that this is going to be more clear now that I explain it, and then we're going to do an example there. But basically what you can do now is look at each source separately, get rid of all the sources in the circuit except for that one, solve for it, and then do that for the next source, solve for it, and then do that over and over again until you cover all the sources and then add all the solutions. And then it's the same thing. Now it seems like, well, that seems like a lot of work. Why do I want to do the same circuit 3 times instead of just 1? It's because if you actually try to solve the linear system, if there's 2, 3 variables, then maybe it's doable. Once you get to 4, you're going to see that it's a lot of work. Maybe the homework has some 1 before. So it starts getting very tedious and very messy. Whereas this approach, as we see examples, it's a lot more circuits, but very simple circuits, because once you remove some of the sources, the circuit simplifies significantly. So it might be an advantage. I'm not saying do it every time, but it's going to be helpful. So that's why it's important. So let me then write down the superposition principle then, which is so the superposition principle. What it says is, so the superposition principle what it says is let B as 1, so that's the first voltage source, and then the second voltage source, and then all the way to, we have n voltage sources. And then we're going to have the first current source, the second current source, and then so on. And then let me have R current sources. Be the complete set of independent sources. This is important, independent sources in a resistive circuit. Then any response and whether it's a voltage or a current response in the circuit, I want to call it Y, can be expressed as have that y is going to be equal to some constant k1 times the first voltage source plus another constant k2 times the second voltage source plus all the way to the nth constant times the nth voltage source, and then plus, say another constant, say k1 hat times the first current source plus k2 hat times the second current source, and then so on. And then k hat r times dsr. So we have n voltage sources and r current sources. And so what happens then is that any responser, so whether I want a voltage across a resistor, a current through a voltage source, anything that I want in that circuit, I'm always going to be able to write it as a linear combination of all the independent sources. So this is important, only the independent sources. So what we see then is here, this independent source has a constant of like this. So if you look at the example that we had out there, I think we had, let's see, we had for that, for example, we had I1 was equal to ds, we had I2 was equal to 1/3 ds minus 1/3 is, and then we had I3 was equal to 1/3 ds plus 2/3 is. And so if we look at that, then there are only two sources in that circuit, and what that means is if I look at the current there, that current is going to be a linear combination of two sources. This is Vs, basically times 1, plus 0 times Is, right? And then this guy is some constant times Vs, and then another constant times Is, and then same thing. So anything that you want in that circuit, voltage or current is going to be of that form. Some constant times Vs, some constant times Is. So all we have to figure out are what are those constants. And what this superposition principle shows is that actually the way you can do this is, because these are completely unrelated to each other, what I can do is, if I want to see what's the response to this first voltage source, what I do is I forget that all of the other ones exist, so I get rid of them in my circuit, and I just leave that one, and then I analyze my circuit, and I will get this term. I'm going to get this term. And then I forget that all others exist except for this one. I analyze my circuit, and then I'm going to get this term. And then so on. And in the end, all I do is just add everything together. That's what the superposition principle is telling. And so we see the first few circuits is not as obvious that this is actually much better. But once we get more complicated circuits, then you see that this might be a very good tool because it simplifies circuits significantly. And you could do resistor simplifications and all the things that you could not do. So we're going to see how this works. So if we look at the same example that we just had, so let's redo that example, but we're going to do it using the superposition method. So what we're going to do then is look at this. So it's the same circuit. I drew it, on the left it's exactly the same circuit that we had before. And then so the first thing we're going to do is look at what happens with just one source. So I'm going to leave the voltage source in there, and I'm going to get rid of the current source. Now how do I get rid of a current source? What I want is basically zero current. So the way to get zero current is just to disconnect it. So what I do is I have this source and I'm going to disconnect it. So that's what I have over here on this side is basically a holder. Right? I disconnected that source. So whenever you have a current source, you disconnect it. Okay? So now this is my circuit. And suppose that let's do this. Let's find Ix. We want to find the current Ix here. Now Ix, if you see, that's a current that was flowing in the top resistor. Right? And if you remember the way we defined the loop currents in the previous example, that's the same as I2. So I2 was going this way. So basically it's the same as finding I2. So we're going to find that current. So let's see, how can we obtain that current? So you guys, it's a simple circuit, so let's try to work this for a couple minutes, maybe 5 minutes say, and we'll see what you guys come up with. So try this on your own, try to find Ix with just this source. of course, it's going to be a function of Bs, right? So Bs is going to show up there. It's not going to be a number. It's going to be something times Bs. Check with your neighbor as well. Make sure they get it. Some people finish,
Yeah, I'm doing the other one with the current source.
so let's see, can somebody tell me what's the answer?
Yes, over three.
Yes, yes. So then this is, okay. So would you mind saying something like that? Or?
So if you have an open circuit, then you just do the outward or outer KVL loop. You do Vs minus Ix times 2 minus Ix times 1 because you know it has to be Ix flowing to that
Right.
final resistor.
Oh, yes, one of them. Yeah. Right. So that's definitely one way to do it. So basically, if you look at these outer loop, then you can do a KVL here and then just solve for Ix. Right? That's basically what happens. So you have the Vs, then so you can do it two ways. You can do say a KVL, right? So you can set this up as a plus minus, and then because this current Ix, right? So this guy is also just going this way because he cannot go through here because there's nowhere to go. So it's got to go the same way to the resistor, so it's the same current, right? So then what we have is the Ds is equal to 2 plus 1 times Ix, and then you solve Ix. So then that's one way. Okay, and then so what happens then when we have the other circuit? I guess you guys need to write this down, right? So let's see what happens when we just look at the current source. And what we need to do is keep the current source and get rid of the voltage source. So what getting rid of it, what I mean is make it 0. Now to get 0 voltage, what we do is we short it. When you have a short, we have 0 voltage. So what we do is then we take this guy and we short it. Right? And so we end up getting the circuit that I have on the right. So we have the cable there on the right. And so same thing. We want to find now, so find the same, find Ix. Right? And so let's see, let's try to find what Ix is. You know it already?
-1/3.
Right. We're going to give people time.
What's the current through the 1 ohm resistor? What's the current through the 1 ohm resistor?
Thought I asked.
Could you say how you got them?
Oh, negative 1/3.
Sorry?
Negative 1/3.
1/3? 1/3, 1/3? Okay. Could you describe how you go in?
Because it's a matrix and there's it's is equal to 0 and you just get the solution. So negative 1/3.
That's probably a So somebody else has an answer.
Okay. Thank you.
No? So it's almost right. So it's actually it's minus 1/3. So let's see how we can do this. So one way is basically what we want is the current here, right? Now if we look at this node, then this current source is injecting current there. So once it injects it, part of it is going to go here, part of it is going to go there, right? Into these two resistors. Now if you look at the resistors, those resistors are actually in parallel because they're connected to these nodes, and they're connected to these nodes, which is the same as these nodes, which is the same as these nodes, which is the same as these nodes. So both of those resistors are in parallel. So we have some current coming into some node, and we have two resistors in parallel. Current division, we can do current division when we have resistors in parallel. So then by current division, so Ix then is equal to, now current division, when we divide the current, then what we do is we have a current coming in and we divide it to currents coming out. So because this Ix is actually coming in, so we put a minus sign to reverse the directions. So that then the current we're looking at is the one coming out. And so we divide the current that's coming in, which is Is, into both resistors, right? And then how do we divide into both resistors? We take the opposite resistance, which in this case is 1 ohm, and then divide it by 1 plus 2, by the sum of the resistors. So we get minus 1/3 of Is. So then from the first part, we obtained that Ix was 1/3 of Vs, and now we know that also it's also minus 1/3 of Ix. So once you have the values for those sources, then you're done. You get a number out of it. So now if you actually look at this, so so total. So these are the two individual contributions. So the total current, total Ix, is equal to then 1/3 Vs, which is what we obtained from the voltage source, minus 1/3 Is, which is what we just obtained from the current source. And then if you look at your notes, and it's actually behind the screen, so I'm going to pull the screen up just when you guys finish writing. But look at what you had write down for I2 when we solved this circuit using the node voltage.
You can also get that by writing the KVL for the super loop, right?
Right, you can do a KVL. Yeah. So there's not a single way of doing it, but you can do it multiple ways. Right. Now the thing is, now if you look at that answer, and you compare that to what we have up here, it's exactly the same thing. Right? 1/3 Vs minus 1/3 Is. And that's exactly what I was telling you. What the superposition principle tells us is we can do this with a full circuit, or we can do things independently and then just add the solutions. We should get exactly the same thing. Yes?
So in this case, though, there are only two sources, so we can just remove one and then the other.
Right.
When there's more, how do we kind of utilize that approach?
Yeah, we're going to do it in the next example. So the next example has 3 sources. But then the idea is basically you can just look at each source separately and then add the solutions in the end. And the nice thing about this is that if you look at how we solve those 2 sub-circuits, then we're pretty straightforward. I mean, they're simple circuits versus doing the node voltage method, which once you start doing the algebra there, it gets messy. So it's a lot more, it's a higher chance, at least for me, to make a mistake there. And so superposition simplifies things. So any questions about these particular examples? Same way. So now the calculation would be different, right? So in that case, let's see if we wanted to get I1. So once you get so I1 and I3, for example, I1, let me go back to that. So this is the linear circuit. So if we wanted I1, then again we use the superposition method, but then we just obtain the current, say for example, I would be the current going through this source here. So it would be this current. So you do the same analysis but apply to the specific source. So it depends on which one you want. Right, for this one you will need it. Now the thing is also that the node voltage method, what it does, sometimes it's an overkill because it will always give you all the node voltages. So what if you don't care about all of them? What if you just want one of them? So what if I only want the voltage in one resistor? Do I really need all of them? So you might be doing a lot of extra work which you don't need. Right? Whereas if you do superposition, you can focus directly on just one of the quantities. So it might be better as well. So it depends on what you want. If you want everything, well, the solution node voltage method will give you everything. But if you just want a part of it, then you might be doing extra work. That's not necessary. Now the good thing about the node voltage and loop current method is that they always work. So it's systematic and it will always work. It's very tedious, but it always works. So when in doubt, go to that one and then you can get the solution. But sometimes it's doing too much work that you don't actually need. But, so that's this example. So let's look at another example, which has now 3 sources. So now the original circuit is the one we have here on the left, and then what we're going to do then is start looking at this one source at a time. So then I'm going to start by keeping this in this example. So what I'm going to do then is look at the case where we keep the voltage source here. So I remove the other 2 sources. Now we have 3 sources, so I need to remove the other 2. Remember, the way I remove a voltage source is I short it, right? So this other source, I'm going to short this guy. And see, now here it shows us a short circuit. And then the current source, here I remove it, and the way I remove it is I unplug it, right? So here I guess it's not as obvious, but there's a hole there. There's supposed to be a hole there. So there's nothing going up. And so that's the way you do it. Remove, disconnect current sources, short voltage sources. So now what I'm going to do is I want this V hat that's labeled here. So I want to obtain V hat. And the way we're going to do it is just using superposition. So now once I do this, then what I want up there is V hat. So again, this is the circuit is not that complicated, right? So how can I get V hat? So V hat is a voltage across these resistors terminals. Here and here. But these are the same terminals as here and here. So these 2 are in parallel, right? The circuit is open on top. Again, it's not that obvious on the top. I guess maybe from your side it does look. So there's a hole there. So there's nothing going up on the top branch, right? Because it's open. So those 2 guys are in parallel. So if we simplify those 2 into a single resistor, then the voltage we have is the same there, right? So what we can do then is write this as a, so we keep the 2 volts here, we keep the 2 ohms here, and then we're going to combine the other 2 resistors into a single resistor, and I still have the hat there. And then here I have a parallel resistor, and then when they're in parallel, since it's only 2 of them, what I do is I multiply them, right, and then I divide by the sum. So I have a resistor which is 2/3 of an ohm, and then I have a resistor that's 2 ohms, and I want the voltage in one of them, right? And now, if we look at this, this is just a single loop, right? The resistors are in series. I have a voltage source. So part of the voltage is going to be in one resistor, part of the voltage is going to be another resistor. I do voltage division. So then by voltage division, then V hat is equal to, so I'm going to divide the 2 volts that I have there, right? And I divide it between the 2 resistors, and for voltage division I use the resistor where I want the voltage, right? So I'm going to use the 2/3 divided by the sum of the resistors, right? 2. And then you end up getting half volt. So that's the contribution from just the first voltage source, right? So I need to find a contribution from the other sources. So then I'm going to switch now to the case where we keep the current source and we disconnect, we short both voltage sources, right? So let's see what happens when we do that now. So what we do then is we're going to leave this current active, and so we're going to short this guy and we're going to short this guy. And so we end up getting the circuit that I had there on the right. Again, we want the voltage there. And so let's see, how do we get the voltage in this case?